Yeah, thank you so much for the introduction. Yeah, I'm very happy to here to present our work. This is actually joint work between our lab and together with UCLA, MIT, and also Arizona State. I also saw my collaborator French with there, so yeah. My students, he couldn't come due to the visa issue. That's why I'm presenting the work. So hopefully I will give the good work, good talk here. Let's talk about the motivation why I want to do this, for the placement of the quantum circuit. So before we jump to the technical details, we actually all have been aware of, the fast growth of the number of the qubit we can integrate on the chip. So you can see the summary, just last about 8 years, we're actually starting from the 5 qubit until more than 1,000. And we are able to build up a lot of logical qubits on the chip, which actually allow us to do a lot of more, instrument work. But the issue is, if you look at, the realistic, the problems we're trying to solve, people told, us like we need about million qubit. Now, if we're starting from the 1,000 to be 1,000 times more, there's still be a long way to go. And the challenge, for implement this, including the following things. The first one is about the noise, right? So currently, for all the existing technologies like, superconducting or the atoms or, spin such and such, the gate error rate is roughly about 10 to -3 or -4. But our algorithm told us we probably need a 10 to -10. We all know, we cannot just achieve the singly built on the devices because of a lot of physics behind this, but we have to actually use some other optimization methods, trying to achieve this target. Okay, so this actually came up, our motivation here. So what we could do, by using our technology in the conventional semiconductor circuit design, which apply to this, the semiconductor look like, the circuit, especially the quantum circuit, to improve the reliability of the quantum circuit. So this basically involve the placement and the route. In the semiconductor, we're familiar with this, right? So we have a lot of logical gate. We're trying to route those things, placing the different corners and make sure we can, have minimize the interference between the different circuits. But for the quantum, can we do the same thing, particularly for the superconducting quantum computers, trying to optimize the connectivity topologies and also, by taking into account the frequency spectrum. So that's why we call the frequency-aware, placement, for the reliable layout. So this will be, what we're trying to do here. I'm sure everybody in this room we're familiar with this particular, diagram. But if we want to build up this artificial qubit by using these devices, we have to build something like this. So when we look at this, we basically have, this qubit pad together with, kind of inductors or also substrate such and such, to build up this qubit and also the resonators. So that'll be the real thing we need to optimize. So basically have a qubit, at the different corners, and we have this resonators, trying to connect them together. So we have microwave pulse to generate this one. In this particular case, we have a fixed frequency for the qubit, and also have linear couplers for this resonator, the design. So that'll be the very, challenging scenario because we'll not be able to tune those things. That's why it gives us, very challenging scenario. We have to, optimize those things, in the placement rather than we can tune the frequencies and such, trying to minimize some challenges such as crosstalk. Okay, so that's the biggest challenge here. Okay, so let's see how we're able to formulate the problem. So we basically have the following things. Number one, we try to have the placement in the quantum circuit domain to determine the physical location of the quantum component. In this particular case, we just talk about the qubit and also the resonator, but we certainly can talk about more, for the difference in like a via, such and such. And also our goal is trying to optimize the substrate area utilization because that will be, determining the upper bound of the frequency we can basically implement on this quantum circuit. And also try to minimize, the crosstalk and ensure we have a high fidelity in the layout by solving the quantum specific, issue like a crosstalk. Okay, there are a couple constraints in our optimization. So for first one, the lower bound, constraints which we call That is, the intercomponent crosstalk and also design rule violations, such as the overlap between the different components. Because we try to define the similar design rule as we use in the semiconductor circuits, trying to make sure they can, we need to inject basically the minimal spacing between different components, to minimize, the interactions. But also the upper bound constraint, because we do not want to have, the spectrous, the mode such as, the large substrate, avia such and such, and because that will determine the maximum frequency we can allow, and also to minimize the chip cost and the resource limitation. Well, usually this may not be the real constraint so far, because we don't really have the large number of the qubit, but in the future that will be. Okay, so those will be a couple constraints we need to consider. So definition, this, the crosstalk can be defined as here. So basically, that will be the interactions between the different quantum components caused by the resonating frequency of the element that's in the different positions, including both the frequency domain and the spatial domain. And what we're trying to is actually trying to find out the mathematical representation, to calculate the coupling strengths in the Hamiltonian, the model, and also consider both inter-qubit interaction and also inter-resonance, interactions. So it's actually a very simple model if you look at this, because we have to have the different component, and you will find out if the frequency are pretty much the similar, that will give you the high crosstalk. Otherwise, if they were deviate from each other, you can see tremendous drop, for this basically the coupling strengths. So we're able to model this, fairly accurate by doing this. So the real model would be like this. You basically have the separation distance between the different transmol qubit, and following the increase with the distance, you'll start to see, the increase in the parasitic, capacitance that will represent, the crosstalk. But if you see the discrepancy between different frequency of the device, then you'll start to see the drop of this, the coupling strengths. So that'll be something like we show here. So if we are able to, embed this analytical presentation in our models, so we can, just do the optimization. And a similar definition you can find out in this, resonator crosstalk. I'm not going to go through all the details. Okay. So for the upper bound, the constraints and ways we just mentioned it, following the increase of the area of the substrate, this frequency will actually drop. So that's why you do not want to do that, because that basically limit, the upper, bound frequency we can, achieve on these devices. So we actually the lower substrate, frequency compromise, basically this will compromise the performance. And also we talk about, the area and also the cost. So let's see how, the Qplacers, optimize this everything here. So the Qplacer is basically including the following components. The first one is the frequency spectrum and the topology. That'll be I consider as the input. We'll talk about this one later on. And therefore including the three different stages, trying to finish the whole design cycles. So first one is the instance, the padding and the resonator partitioning. And then we have a frequency-aware placement optimization. And after we have done all these optimizations, we have component, legalization to make sure, the layout will be, practical and feasible. So the first one is the input. We actually can represent, what we designed by using this diagram. So basically, the circles, represent the qubit, and also resonators are represented as a rectangle. And for the different sizes, it actually represent, the different real, the areas occupied on the chip. And you have a different colors that also represent different frequencies, because that will participate in, the representation of the frequency. And also you have a color coded for all this stuff. And this topology will represent, what we're going to do on the real circuit design. So we have a padding. Padding actually is actually a very typical operation. Whenever you have one device, you want to make sure you're going to pad the areas larger than the device is going to be, because you want to reserve the spacing between different components. For example, you have a 300 micron in the device. You want to have the spacing for the 600, so you basically need to increase the both margins are running the different side of the device to the 600 to make sure you will have this the gap. And you can do all over the things to increase the layout as we show here to make sure you have this. And the second one is actually the padding can only apply during the placement, because after you increase the area, so the placement will consider as this one as the occupied area to make sure you will satisfy the spacing requirement. That's also the design rule you're going to have. Okay, this will be very interesting. So if we have a resonators, we have to have this space requirement. And also you can actually chop this resonators to different smaller segments and also rearrange them. Because what I really care is about the length of this resonators that give you the basic definition of the frequency, but you can really arrange them in the different shape. And why we want to do this? Because for the different shape, that give us additional flexibility to do the placement route. And if we can do this, we're actually going to have another dimension of the flexibility. We're able to optimize the layout, and that will give you the better result, and we show here. So we're basically trying to allocate the space, by using this partitioned, smaller, component or the rectangle to do this work. Okay. So if we have all this, now the next question is how we can optimize this. We have the multiple objectives. In this particular case, we have a frequency force objective. It's basically trying to compute the interactions between different components by using this. This is a relation between different devices. We can model here. And we try to mitigate, the crosstalk, by modeling those things. So in particular, we have this equation here to calculate the relationship between the crosstalk and strength, as well as the distance, or basically relative position of the different devices, and we show here. So, and this actually used in our optimization process. So we actually try to optimize everything to find out, the global optimization by doing this. And also another thing is about the component density, because we try to minimize the overlaps between different components. That's also another way we're able to guarantee the design rule while still minimize the substrate areas, and we show here. And also including the wire length, because we need to connect everything together. They'll be also considered as a part of the constraints, and we show here. So the final step, we do the legalization. So if we have everything there, so the qubit will be actually treated as a Markels, and a resonant space segment are treated as a standard cell. And we're actually trying to standardize everything here. And the process will be digitalize the qubit first, followed by the resonate. So you have some component, followed by the connections. And the resonance regularization merge and partitioned space segment back to the contiguous block, because eventually you still want to occupy this area, and you put the resonate on top of this. Okay. So let me give you the animation to show how this is going to work. You start with very dense stuff, but then we'll try to distribute everything together. And you're basically trying to define the required substrate area, as we have done in the semiconductor circuit, to see if you are given with areas, if we're able to place everything within this area. The blue will be the partition, resonate, and the red one will be the qubit, as we show here. Okay, you can see actually work very well. And the result is basically showing that, if we consider the program successful rate, this is something like, how likely you're able to program, your quantum circuit, in our design. So the higher value indicate the better performance of the tools. And you'll evaluate over 50 random mapping for each program. You'll find out our result with the Qplacer here always achieve very high success rate. You also see that the human can do similar, performance at visual here. In some cases, better because the human design considered as a golden, result. So you can spend time on this, to really optimize by doing it. But we are trying to automate the whole things. We use, the tools to minimize the software, inference and make sure we have the same baseline to compare with. And also the AVIA, so the classic, the placer basically showing the, relatively conservative result I'm going to show here. And actually our result is the AVIAs. In most of the cases are similar to the, the human designed one. And but human usually, gave us the, gave us similar or, the better result, but that's fine. But Qplacer outperformed the human design with, sorry, actually, let me take it back. The classic will have the similar AE areas, and the human design will occupy, the larger areas because they generally cannot explore all the possibilities in the optimization. So we basically save the area by more than 2 times. Okay, so concurrent. We actually, introduced this crosstalk in our different domains and formulate. And we use the Qplacer to optimize everything and also outperform the human design, the layout in the area efficiency and also to achieve the higher fidelity. And we believe, this placement problem is critical, but it's also under easy challenges. And we call for, attention to this particular domain. And the future direction could be just adding the more challenges, more realistic one, like decoherence, the leakage, such and such, which we had not considered, and also including more components like vias, control lines, such and such, and also the rational routing is basically beyond, we do the placement has to now be considered. That should be the future work. Okay, so I conclude my talk. Thank you so much.